A thin, non-conducting rod with a uniform distribution of positive charge Q is bent into a circle of radius r to make a ring. The central perpendicular axis through the ring is a z-axis with the origin at the center of the ring. What is the magnitude of the electric field due to the rod at z equals 0 and z equals infinity? Let's start this problem by sketching our own picture. We will start off with the ring of charge. And this ring of charge has a magnitude of charge equal to Q. Let's place the central axis of this ring of charge such that it is parallel to the z-axis. We will place the origin of this ring of charge such that it is right in the center of this ring. Here's our x, y, z coordinate system where the y-axis is horizontal, the x-axis is coming towards us, and the z-axis is vertical. The problem is asking us to find the electric field at two different points. One point is at the origin, and another point is infinitely far away. So instead of solving two problems, let's really treat this as one problem. So instead of solving the special case for z equals 0 and the special case for z equals infinity, let's pick an arbitrary point on the z-axis. This point right here. And that arbitrary point on the z-axis, well, we could say that that is some point z equals a. I'm just using the constant a there because I am currently fixing the point, but we're going to be allowed to vary that at a later point. This ring has a radius of capital R. So I will indicate that in the sketch. And in order to find the electric field at that point on the z-axis, and the cool thing about having that point, we could set z equals to 0. We could set z equal to infinity. We could set z equals to 1 meter or z equals 1 femtometer. We're able to vary the position of that. So we'll be able to come up with a general expression for the electric field and apply it to parts A and B. But in order to do that, we need to dissect this ring into bits that we know how to work with. Remember, we already know how to calculate the electric field due to a point charge. The electric field due to a point charge as a function of the distance away from that point charge is equal to k, q being the value of the charge, the point charge, over r squared. The problem is this is only for point charges. A ring of charge isn't a point. This ring occupies 2 dimensions in space. And because it occupies 2 dimensions in space, we can't directly apply this formula for a point charge. We can't directly apply it for this ring of charge. But we can indirectly. Since we know how to calculate the electric field due to a point charge, let's break this ring of charge into an infinite number of tiny point charges. So I am going to create a representative charge element, and I'm exaggerating the size of this charge element to make it easier to visualize when we calculate the electric field here. But this charge element right here is going to represent part of the whole. It's going to represent an infinitesimally small amount of charge, dq. And dq will be our representative charge element. What we're going to do with dq is we're going to take that dq and sum up all of the other tiny charge elements all the way around the ring. That dq is a certain distance away from point A. So I'm going to add that to our diagram with a dotted line. I'm going to draw a dotted line directly from the point on our z-axis to our representative charge element. The reason why I'm doing that is because I know electric fields point radially away from point charges. If we assume that our charge Q is a positive charge, then dq is a positive amount of charge, and so we can draw a tiny representative electric field element pointing radially away from our representative charge dq. And so since this is a tiny bit of electric field, I am going to represent this piece of electric field as dE. This piece of the electric field is a distance r, or let me rephrase that. The point at which we're calculating that electric field is a distance r away from our representative point charge. What you might be noticing that I'm doing here is I am creating a right triangle, which will give me information that will help me to calculate the electric field due to this entire ring of charge. But now that I've sketched my representative charge element, let's apply this to the formula that we know for calculating point charges. The electric field due to a point charge is equal to kq over r squared. Well, since we have a tiny piece of charge, this is going to be a tiny amount of electric field is going to be equal to k over r squared dq. This is a good starting point, and after my sketch, this is usually where I begin the problem. Now, every piece of this right here should have a home in our diagram. So notice the electric field, the dE, is sketched in our diagram. R, the distance from the charge to the point, is in our diagram, and dq is in our diagram. We want to turn this tiny bit of electric field into an overall electric field by summing up all of the pieces of charge that contributes from the ring. So in order to do that, I'm going to draw another sketch to help me out. This sketch is going to have a side view perspective. So here's the side view of my ring of charge. In this side view perspective, it doesn't matter that we're on an x-axis or a y-axis or a z-axis, really. And here it could only be x or y since our ring is in the xy plane. What matters, rather, is that we are some distance from the center of our disk. So you could put a y-axis there if you want. You could put an x-axis there if you want. But the problem, why I'm going to call this the r-axis, is because I'm just concerned with the radial portion of this electric field. So I am really treating this as a polar coordinate type of problem. Since a ring has circular or polar symmetry, I'm going to choose to use polar coordinates to help me solve this problem. So one thing you should always be aware of, try to choose a geometry or try to choose a coordinate system that matches the geometry of your charge configuration. I'll write that here. Try to choose a coordinate system to match the geometry of the charge configuration. Since here we have a ring of charge which has polar symmetry, and you can see that we have polar symmetry if we just take another vantage point, a top-down view looking down from the z-axis. Polar symmetry. Since this ring has polar symmetry, let's go ahead and use a polar coordinate system. And so when I go and look at this image that I've drawn on the left, that means the z-axis is straight up, and we have the r-axis from the side. Now, what I accomplish with this is it allows me to take a different view of my ring of charge. It allows me to take a different view of my charge element. So let me draw my charge element right here at the end. And let me redraw from this side view what the electric field looks like at that point. So here is DE. And from this view, we see clearly that we have a right triangle. And this right triangle has a horizontal leg that is just the radius of the ring. And it has a vertical leg that is equal to our point on the z-axis at the point z equals a. This ring of charge also has a fixed angle, or at least the representative charge element has a fixed angle because it's always at the perimeter of the ring. The angle that the electric field makes with the xy plane will be constant. This is important pieces of information because what this allows us to do is it allows us to start representing various variables in terms of each other. So for example, the distance between our representative charge element and the point on the z-axis is given by Pythagorean's theorem, which tells us that that distance is equal to a squared plus r squared underneath the square root. So by changing our perspective on this picture, we're able to start creating relationships between the different variables. Because one of the things you want to try and do that I'm going to write down because it's so important, one of the things you'll want to try and do is express the variables in terms of your coordinate system. So I will say, if possible and convenient, it's a good idea to express your charge, dq, in terms of the coordinate system chosen. So if we had a rectangular coordinate system, which involves the x, y, and z axes, we would try to express our representative charge dq in terms of x, y, and z. If we had a spherical coordinate system, which if you've had multivariable calculus, you know what a spherical coordinate system is. If we had a spherical coordinate system, we'd want to try to express the charge in terms of rho, theta, and phi, which is a distance and two angles. Here, we chose a polar coordinate system. And we chose a three-dimensional polar coordinate system, often called a cylindrical coordinate system. So this polar coordinate system, we're going to be worried with a distance in the xy plane. So I don't want to use too many of the same variables because we're calling r for one thing, and in polar coordinates, we'll often call this distance from the center to our circle lowercase r. Fortunately, our circle has a constant radius, so we could use the variable capital R for this. But in our polar coordinate system, we would have r, which is a distance in the xy plane from the origin. We'd have an angle theta. Theta is measured counterclockwise from the positive x-axis, so that theta would look like this. And we would have z, which is measured along the z-axis, and this is our triplet that represents a point in a three-dimensional polar coordinate system. This is the coordinate system I'm going to use because I'm going to suspect that solving the problem will be easier, which is why we always want to try and choose a coordinate system to match the geometry of the charge configuration, because you can often simplify the calculational tasks. Let's copy our coordinate system to the next page. So now that we have our coordinate system drawn, let's remember that the tiny representative charge element we're working with is k over r squared dq. We have r expressed in terms, and that's lowercase r, the distance from the representative charge element to the point we're interested in. We have that distance represented in terms of polar coordinates, the a squared and the r squared. So we could write r squared is equal to a squared plus r squared, both values that we have to work with. R is a constant, and a is really z. We could equivalently just call this z squared plus r squared if we wanted to. But now let's represent our representative charge element in terms of our polar coordinate system. So we have to figure out what dq is. So to determine dq, let's go back to that top-down view looking down from the z-axis of our coordinate system. So if we're staring right down the z-axis of the coordinate system, the ring of charge looks like a circle. Let's place our representative charge element at some arbitrary location here. I will place our representative charge element right there. The reason why I've switched to this perspective is it's going to help us determine what our representative charge element dq is. And I'm going to exaggerate that representative charge element a little bit. Now, in order to find what that representative charge element is in terms of our coordinate system, in terms of the geometry of the problem, we should turn to what we know about charge density, because charge density provides the connection between the charge and our spatial variables. Remember, the linear density of a line of charge is equal to charge per unit length. So we know that we have a uniform charge distribution, so lambda is a constant. Let's go ahead and rearrange this so we could express dq in terms of lambda, our constant charge density, and the tiny length of charge that we have. Well, that tiny length of charge comes from the dq here, and let me label my picture. Here is our dq, and our tiny length of charge is this right here. I will call this dl. So what do you think dl is in terms of polar coordinates? Well, it would probably help that if I drew the radius in here, so that's r. And we know that tiny bit of charge takes a tiny bit of arc. So this tiny bit of arc is a tiny angle that I'm going to call d theta. Theta is the angle from the positive x-axis to our charge. And that the extent through which the arc through which the arc and our tiny bit of charge spans an arc length of d theta, a tiny bit of angle. So dl is really given by the arc length formula. R is our radius times d theta. Now that we have our tiny bit of charge in terms of L and our tiny bit of length in terms of the radius and theta, which are our polar variables, we can now write the representative charge element as lambda r d theta. And this means that the electric field due to a tiny charge element is equal to k over r squared times lambda r d theta. Oh, this is nice because we have a single variable to integrate over. R, lowercase r, is a constant. It's a constant because we're looking at a single point in space, the point at A on the z-axis, and the radius of our ring is constant. Oh, and this is r squared, so I don't have to put that under a square root. And then in the numerator, we have two more constants, lambda and the radius of the ring, and we have that tiny bit of angle d theta. This is looking really good. We only have one variable of integration, and this would tell us the electric field due to that infinitesimally small length of charge. Unfortunately, we don't have that one tiny infinitesimally small length of charge. We have a ring of charge. So we're going to have to sum all the way around the ring. And electric field is a vector. So we have other components to deal with. In this picture, we have an R component and a Z component to our vector. And well, let me show you what that R component and the Z component is. So in our picture, the R component of our electric field vector is just that component of the electric field that is parallel to the radial axis. So I will call this dE sub R for the radial component of the electric field, parallel to the radial axis. And we have a vertical component of the electric field parallel to the z-axis. I'll call that dEz. Now, from alternate interior angles, I know that this angle right here is also an angle theta. So the electric field being a vector, and since we have to sum over all of the infinitesimally small electric field contributions, we're going to have to take into account the components of this electric field, the Z component and the R component. So is there a way that we could simplify this problem to make the calculation a little easier for us? Well, if you said use symmetry, you'd be exactly right. The great thing about our diagram is we could see one fact. Every charge element is going to have a mirror element. In this bottom picture I sketched, that charge element in the first quadrant has a mirror charge element in the third quadrant. That mirror charge element has its own amount of charge that is equivalent to the infinitesimally small charge on the other side. The only difference is on the opposite side of the origin. And because of that, the electric field due to that mirror charge is going to be a mirror image of the electric field due to our original charge. If we take that information to our upper sketch, where the mirror charge is right here, in our upper sketch, that means we have the electric field due to our mirror charge will look something like this. And I'll just put a prime on this one to specify that it's due to another charge, due to our mirror charge. And I'll just call our mirror charge dq prime. And the thing is, dq prime is equal to dq. I am just using the prime to signify that that is our mirror charge element. Looking at our diagram now, that mirror charge element, the radial axis is going to offset, it's going to counter the radial component of our original charge element's electric field because of symmetry. That mirror symmetry about the z-axis, for every charge element, there is another charge element on the opposite side of the origin, such that the radial component of the electric field vector will cancel out. So what that means for us, we're not going to have to worry about the radial component of the electric field. The only thing that is left over is the z component of the electric field. And earlier I called this dEz prime for the magnitude of the electric field due to the mirror charge. I really should have called that just dE prime. And I just drew the vertical component of the electric field due to that mirror charge element. And this is what I meant to call dEz prime. Let's take a look at this now. We have two of these z components of the electric field. Notice they're just all going to sum in the positive direction. And notice the radial component of the electric field will cancel each other out. So another good point to remember is use symmetry if it's present. Use symmetry to simplify your calculation. We now know we only have to calculate the z component of the electric field. Let's look at what we have. So if we only have to calculate the z component of the electric field, that means we just need dE sine of theta. Now we have the z component of the electric field due to our charge element is equal to the magnitude of the electric field of our charge element times the sine of the angle theta from trigonometry. We know from earlier that the electric field due to that representative point charge is k lambda r over r squared. D theta, and that is multiplied to sine of theta. This means that our z component of our electric field, which is our total electric field because we don't have an r component due to symmetry, the z component of our electric field is equal to k lambda r over lowercase r squared sine of theta d theta. Oh, well, I think I'm getting in trouble here because earlier I called theta to be the angle between our radial line and the ring. And then when I introduced this ring from the top-down view, I reused that same angle theta. But the theta that I used for the ring, for the charge element right here, is different than the theta that I used right here. So that could be very confusing, and it would end up with us getting some wrong values, some wrong work. Or rather, So we have to resolve that mistake because we are mixing variables that have different meanings. Let's go ahead and call this variable that is in the xy plane, instead of calling it theta, the variable in the xy plane, let's go ahead and rename it to be phi. So everywhere we have that d theta, we're going to replace it with a d phi. So we have d theta here, that should be d phi. We have d theta here, that should be d phi. D theta there, that should be d phi. D theta here should be d phi. Now this sine of theta remains theta because that comes from this picture we drew up here. So sine theta remains sine theta, but d theta becomes d phi because that is a different coordinate axis. Okay, so now we have everything expressed as we should. We have the charge, the z component of the charge. We have lowercase r. Well, let's go ahead and replace lowercase r with what we know it is in terms of a and capital R. So lowercase r squared is a squared plus r squared. And then we have sine theta up top, d phi. Well, sine of theta is a constant because remember, theta is a constant. The angle between the charge element and the point, the angle the electric field line makes with the xy axis, or the xy plane rather, that angle is constant all the way around the ring. So that means sine of theta is a constant, a is a constant, we're looking at a single point in space, and capital R is a constant. So we could pull all of those constants out of the integral. And look at how simple this integral becomes. It is just d phi. Now that we know d phi, the next task is to determine the limits of integration. Well, let's just quickly redraw the top-down view of our sketch. So here is our xy axes. Remember, the representative charge element was right about here. And drawing the radial line from the origin to the representative charge element, that makes an angle of phi counterclockwise from the positive x-axis. And if we want to determine the full amount of the electric field, we're going to have to integrate all the way around. So phi ranges from 0 to 2 pi. That means our limits of integration will go from 0 to 2 pi. This is such a simple integration, and what makes it simple is the fact that we are integrating in polar coordinates. So this is k lambda r over a squared plus r squared sine of theta not d phi anymore, we just integrated. So that would just be phi going from 0 to 2 pi. This now is k lambda r over a squared plus r squared sine of theta times 2 pi. We're almost there. There's a couple of things we don't know, though. We don't know lambda, or we weren't given lambda. We were just given that it was a uniform charge density. And we weren't given sine theta, but we have a relationship that will help us determine sine of theta. So really, we have about everything we need to finish this problem. Let's look at lambda. We were told it's a uniform charge density. And by definition, charge density is charge per unit length, dq over dl. So that means, and since this is uniform, the density is constant. So that means that our density is the total charge over the total length of charge. Since our ring of charge is a circle of radius a, the total length of charge is just the circumference of the circle. This becomes q over 2 pi r. So that's what lambda is in terms of the givens. And now let's look at sine theta. To look at sine theta, let's return to our previous graph. So right here, notice that we have theta. We have the this right triangle here. We have a horizontal component, or a horizontal leg to that right triangle is the radius of the ring. The vertical leg of the right triangle is our point A on the z-axis, and the hypotenuse of that right triangle is the square root of a squared plus r squared. We could use trigonometry to determine the sine of the angle. So in using trigonometry, I'm just going to draw my triangle that represents the bits of information we have. This leg is r, this leg is a, and this leg is a squared plus r squared. And this is the angle theta. So from trigonometry, we know the sine of the angle is equal to the opposite side divided by the hypotenuse. Well, putting all of that together, let's copy this line from above. Putting this together, we have the electric field along the z-axis is equal to k lambda r over a squared plus r squared sine theta times 2 pi. Well, then this becomes k lambda r, I'll put the 2 pi here, divided by a squared plus r squared times, now this piece is the sine of the angle, times the sine of theta, which is a over the square root of a squared plus r squared. Oh, and this isn't dE, this is now the electric field E. Let's simplify this now. Again, we know lambda, oh, look at this. We know that lambda is equal to 2 pi r. We know the Coulomb constant is really equal to 1 over 4 pi epsilon naught. The epsilon naught is the permittivity of free space. So I see where we could simplify some things here. So we have the k, which is 1 over 4 pi epsilon naught. Lambda, which is q over L, and L is 2 pi r, times r times 2 pi times a, all over a squared plus r squared to the 3 halves. Well, it looks like there's a few things that we can cancel out. The 2 pi in the numerator cancels with the 2 pi in that denominator. The r in the numerator cancels with the r in the denominator. And it looks like I might have gotten overly aggressive with the k, because I'm not seeing where that's going to cancel anything. I was thinking it was going to cancel that 2 pi in the numerator, but our linear charge density, q over 2 pi r, ended up canceling with that. So I'm probably going to recall that k for simplicity. This means that we have the electric field is equal to K A Q over A squared plus R squared to the 3/2 power. And this represents a point A on the z-axis. So being a vector, that's in the k-hat direction. Now let's go ahead and do a unit check to make sure everything works. If the units don't check out, then I made a mistake somewhere. So the mistake could be in the unit check itself, but it would probably be most likely in my algebra somewhere. So let's do the units. The units of the electric field is a Newton per Coulomb. The unit of K is the Newton meter squared over Coulomb squared. A, which is a position on the z-axis, has a unit of meter. Q, our charge, has the unit of coulombs. This is over under the 3/2, we have essentially a meter squared from both the a squared and the r squared. I see that the square root of the meter squared in the denominator will cancel out. And then I see that I have a meter cubed in the numerator, which cancels with the meter cubed in the denominator. I see I have a coulomb in the numerator, which cancels with one of the coulombs in the denominator. I end up with a Newton per Coulomb, which is great. The units check. Since the units check, I could be reasonably confident in my answer that I at least didn't make a major mistake. So I am now going to say, well, Z was equal to A. So I'm now going to say the electric field as a function of Z, and again, we are restricting ourselves to the z-axis, is equal to K ZQ over A squared plus R, and that A is a Z, Z squared plus R squared to the 3/2 power along the z-axis. This is our answer for the electric field due to this ring of charge. You're probably wondering, why did we express this in terms of Z when part A says find the value of the electric field at the origin, and part B says find the value of the electric field infinitely far away? Well, the reason why is if we didn't solve this generally like we just did, we would have to do twice as much work because we would end up finding the special case of the electric field at the origin, and that would have dictated everything we did. And then we would have had to find the special case of the electric field infinitely far away. And to find it infinitely far away, we'd probably still have to use this technique anyway. So this allows us to free two birds with the same key. Let's look at this. Here is our result. Part A says, find the value of the electric field when Z is equal to 0. So in other words, we want to find the electric field when we are looking down from the z-axis. If this is the ring of charge, as we've discussed earlier, if you look here, the value of, let's look at this. Looking at the equation, you could probably very readily see that when you plug in 0 in our equation, that you get 0 for the electric field. And let's go ahead and do that so you can see. The value of the electric field when Z is equal to 0 is equal to, well, 0's in the numerator. Doesn't matter what's in the denominator as long as it's not 0 too. So the electric field at the origin is 0. Now that makes sense graphically. We would expect that, because if there is no z component, every infinitesimally small piece of charge on the ring has a mirror charge on the opposite side of the origin. And if we are only looking in the xy plane, the mirror charge's electric field vector will exactly cancel with its opposite. You can go anywhere. You could go here. This charge here would have an electric field directed that way, but its mirror charge element would have an electric field that's opposing it. Here at the bottom would have an electric field vector pointing up, but at the top would have an electric field vector pointing down. So when you sum up all of those charge elements, we get a net result of 0 electric field when we are at the origin, when Z is equal to 0. So that's a great reality check. Our graphical sketch there helps confirm our computational answer, that the electric field should be 0 at the origin. Well, let's do another reality check. What is the electric field when we are infinitely far away, at a point when Z is equal to infinity? Well, let's look at that. If Z is very, very far away, so imagine, let's see what we would expect. What I would expect is, if we go very far away, is I would expect the charge configuration to look more and more like a point charge. Actually, let's go ahead and sketch our charge again. My expectation, our expectation, should be that the farther away we go from that ring of charge, it'll look less like a ring and more like a charge. So for example, if we are really close to that ring of charge, it is clearly two-dimensional. But if we go farther away, that ring of charge is going to look smaller and smaller and smaller and smaller and smaller and smaller, and eventually that ring of charge will look like a point charge. So my expectation is when Z goes to infinity, when we get very far away, my expectation is that the electric field is going to look like the electric field of a point charge. That's my expectation. Now, my expectation is also that if z were infinity, that this will approach 0 as well. Because as you know, the electric field follows an inverse square law. So if we're very, very far away, the electric field is going to go to 0. But the next reality check is just to see if it looks like a point charge. So how I'm going to do that is I am going to write our electric field as a function of z, and let's say that z is much greater than r. If z is much greater than r, then we could neglect r. That means the denominator is essentially z squared. Now, simplifying this a little bit, we have z squared cancels with the square root, and notice we have a z in the numerator, cancels with the z cubed in the denominator. So what we have left over after doing all of that is our electric field on the z-axis is kq over z squared. Just like we expected that the electric field along the z-axis should look like a point charge when we're very far away, or at least far enough away such that z is much, much bigger than r. If we now do the limit as z goes to infinity of kq over z squared, we end up with 0. And this is a great reality check that our mathematical results confirm our expectations, and our expectations are confirmed by the mathematical results.